Hello, are there any questions? Let me finish that. I think we finished chapter 2. Let me check. Yeah, we talked about hydrogen bonds. All right. Open chapter 3. Okay, I'm not hearing any questions, so let's begin. Where is the... Did I lose you guys? Oh, here you are.
Hear you.
All right. You should be seeing my screen now. Why is that not moving? All right, so today we're supposed to be starting chapter 3, observing microorganisms. And let me remind you, next Wednesday we'll have our second quiz. There were a little bit of problems with quiz 1, but not too bad. And then tonight we'll be at Thursday in the lab, we'll be discussing lab 4 on stains. Any questions about what we're doing? If not, let's move on to chapter 3. Can you guys see this slide?
Yes.
Thank you. So chapter 3, observing microorganisms. As always, I give you a slide giving you the major goals and a rough outline. Know the terms, know what is resolution, refraction, what are stains, what's a basic and an acidic dye or a basic and acidic stain. How do you make a smear preparation? What is a smear preparation? What is a mordant? And what is peptidoglycan? These are the major terms for this lesson. And then understand the sizes of organisms and the properties of microscopes. Understand the major differences between a light microscope and an electron microscope. Understand why staining improves resolution. You should also know about stains that there are 3 types of stains. There's a simple stain, a differential stain, and then special stains. We'll talk about each of these 3. And then lastly, we won't cover this today, but we'll on our next class, we're going to discuss the Gram stain, and you need to understand it, its procedure, and the basis for its differential staining. Any questions about what we're doing? All right. So when we're observing microorganisms, you need to understand the units that we measure them with. And to measure a microorganism, we use the metric system. Well, the metric system is rarely used in science and medicine, so you should know it for that reason alone. You should know all of the units here and almost all of the units down here. Let me blow this slide up. So you should know that 1 millimeter is, no, that's 1 meter, sorry, is equal to 1,000 millimeters. And then 1 millimeter is 1,000 micrometers, or 1 micrometer is 1/10⁶ meters, meaning a negative meter, negative exponent. You should know a nanometer. Now, a micrometer is the size that we use to measure things under the microscope. And a nanometer is the size of things that we use to measure things under an electron microscope. So you do need to know the nanometer and the micrometer. Now in this table here, you should know a kilometer. A kilo is 1,000 meters. Let's see if I can blow that up a little. You should know a meter. There are units in between a meter and a kilometer, but we don't use them too much. In fact, science doesn't use them too much. A meter is the basic unit of length in the metric system. You should know a centimeter. There is a decimeter, but you don't need to know that one. A centimeter is 1/100th of a meter. You should know, and a centimeter is something you can find on a ruler. Let me see if I can find a ruler. I used to have one over here. Not finding it. You should know a millimeter. That is the smallest unit on a ruler, the metric side, a millimeter. You should know a micrometer. Well, let me say a centimeter is 1/100th of a meter. A millimeter is 1/1000th of a meter. A micrometer is 1/1,000,000th of a meter, meaning 1/10⁶. A nanometer is 1/10000000th of a meter, or 1/10⁻⁹. You don't need to know a picometer, but if you're curious, it's 1/10⁻12. And when we're talking about exponents there, this is the numerical calculation. It's where you have the decimal place over 12 places from the 1. Any questions about any of that? You should know how to convert from metric units to other metric units. And the easy part is it's all based on a 10, a system of 10. So as long as you know the unit, a kilo is 1,000, then you can even convert. We use meter for the length, and we use gram for the weight or the mass, and we use liter for measurements of liquid volume. You do not need to know the equivalent of metric to English, like 0.394 inches equals 1 decimeter, which most people don't know. What's the one I used to know? Oh, here it is here. 1 inch equals 2.54 centimeters. You don't need to know that. Well, never asked you how to convert from metric to English and English to metric. You just need to know how to work in metric. Any questions about any of that? Now, metric is also good, besides being in a system based on 10, it also is a logical system in that 1 cubic millimeter of water is equal to 1 gram of water. And if you were talking about British thermal units, which is part of the metric measurement of energy, which you don't need to know, you use 1 British thermal unit of energy to heat 1 cubic centimeter of water by 1 degree. Let me see if I can remember the other connection. Oh, yeah, it's 1 millimeter of water is equal to 1 cubic centimeter of water. So they're all interconvertible, at least with water. Any questions about any of that? All right, here is one reason why you need to know the metric system. When we're looking at the countries in the world, this map is showing you all the countries in the world that do not use the metric system. And as you can tell, there's only 3 countries in the world that do not use it. There's only 1 big country, which is the United States. All the other countries in the world use the metric system. You should also know the metric system because science and medicine use the metric system. Any question about any of that? For your information, the United States is slowly converting to use the metric system. This was mandated by Congress and signed by the President of the United States. And I think it was President Jefferson, meaning our 3rd US president, who signed this bill to convert our units of measurement into the metric system. And we're going very, very slowly. But if you know, you drive down the street, you usually will see a sign telling you the speed in English and the speed in metric. And then on most cars, it'll give you the speed in both, or at least new cars, it will give you the speed in both English system and a metric system. Any question about any of that? All right. So you should know the typical sizes of microorganisms. Most prokaryotic cells are about 1 to 2 micrometers large. Now this is saying the range is from 1 to 10. And I don't know who made this range up because the smallest prokaryotic cell is 0.4 micrometers in diameter. And the largest prokaryotic cell, I used to know this, it's a little larger than 10 micrometers. Most prokaryotic cells, like I said, are of size 1 to 2 micrometers large. Eukaryotic cells are about 10 times the size of a prokaryotic cell. And this is saying the range is from 10 micrometers to 500 micrometers. I don't know the size of the smallest eukaryotic cell, but I do know the size of the largest eukaryotic cell. And the largest eukaryotic cell is the yolk of the ostrich egg, which I don't know the size of that, but the yolk of a chicken egg is about that size, okay? I don't know what that is, almost an inch, a little smaller than an inch maybe. And that's the largest cell that most of you have ever seen. Has anyone ever seen a cell larger than the yolk of a chicken egg? That would be the yolk of a turkey egg or the yolk of an ostrich egg. Ostrich eggs are very rare, so most of you wouldn't see that. I have had one student who did see the yolk of a turkey egg, and that would be even larger. Viruses are smaller than that, and they're about 10 times smaller than a prokaryotic cell. The smallest virus is about 0.02 micrometers in diameter, and the largest virus is about 0.44 micrometers in diameter. Now, usually when we're talking about viruses, we use nanometers because they're so small, in which case they'd be 20 nanometers to 440 nanometers. You'll note that the largest virus is about the same size as the smallest prokaryotic cell. And we're talking about diameter of the virus. When you talk about length, we go even larger. The Ebola virus is the longest virus. However, it's really skinny. So its width is only 0.02 micrometers wide, but the length reaches up to about 1 micrometer long. So it's actually not the largest virus by diameter, but by length it is. And that's Ebola, the longest virus. Megavirus is the largest virus we're going to talk about in the class. And it's about 0.44 micrometers in diameter. All right. So to see microorganisms, what do we need to use to see them? Come on, you guys know this.
Microscope.
Yeah, you need a light microscope to see most microorganisms, actually all microorganisms. For all prokaryotic cells, you need a light microscope. For most eukaryotic cells, you do need a light microscope. However, frog eggs are a eukaryotic cell, and they can be seen with our human eyes. And then chicken egg can easily be seen with our human eyes. You should know the relative rank of the sizes here. Let me blow this up. So you should know a person is bigger than a chicken egg, bigger than a frog egg, bigger than a eukaryotic cell, bigger than a prokaryotic cell, a bacteria, bigger than a virus. A virus is bigger than a large molecule like a protein, which is bigger than small molecules like water, which is bigger than atoms. Now, to see the small things, we need a light microscope. You can use a light microscope to see about up to 100 micrometers, but that's overlapping with the light microscope. All right, any question about any of this? You don't need to know the measurements of the different objects, but you should know the rank. And do note that I've made a correction in this slide here. That shouldn't be 1 micrometer. That should be 1 millimeter right here. There's the micrometer right here. Remember that when you're going through your textbook, that this graph has a mistake in it, and the author never corrected it. In the custom edition, we've had 3 custom editions. In the textbook, this error has gone on for 12 editions. All right, let's talk a little bit about the light microscope. You're viewing a compound microscope. That is a light microscope that has 2 lenses or more that magnify. In most compound light microscopes and all the compound light microscopes in the lab, we have an ocular lens that magnifies and an objective lens which magnifies. The total magnification is the objective lens times the ocular lens. So if you use the 4x objective lens, the magnification will be 4x times the ocular lens. Most compound microscopes have an ocular lens of 10x, but some have an ocular lens of 20x, the most expensive and the best, I guess. In our lab, all of our ocular lenses are only 10x. Typical compound microscopes have for objective lenses a 4x objective, a 10x objective, a 40x objective, and a 100x objective lens. But different microscopes might have different lenses. I actually own one that only has 2 objective lenses, and I think it has 10x and 40x for the objective lenses. Now, you don't need to know that. You should just know. Typically, we'll work with microscopes. You'll work with them in the labs with 4x, 10x, 40x, and 100x objective lenses. You should know the different parts of the light microscope. Most of the parts shown here, you should know the ocular lens, maybe the body tube, the arm, which isn't labeled here, you should know that. You should know the objective lens right here. You should know the stage, which isn't labeled here. Let me see, the stage is labeled here. The specimen, where it goes, the condenser, the illuminator or lamp, the base of the microscope, the ocular lens, the body tube or the arm, the objective lens, the stage, the condenser shown here, and then the iris diaphragm shown here. I think on the previous lab, these two were in reverse position, and the iris diaphragm has a lever on it. Let me blow this up. It allows you to open and close it. There, you can sort of see the lever right there. And that opens up the shutter for the iris diaphragm or closes it down. The illuminator or lamp, you should know the coarse focus and the fine focus. Any question about any of that? All right. You should know how a compound light microscope differs, shown here, from a simple microscope shown here. A simple microscope is one that only has one magnification lens. So a simple microscope, really all it is a super duper magnifying lens. And this is a microscope that Antony van Leeuwenhoek made, which was a simple microscope. Any question about any of that? All right, you should know the resolution is the ability of the lens to distinguish 2 points. Let me show you in the next picture. So these 2 objects, we'll call it that, 2 points, can be resolved. Here is the magnification under the microscope, and I don't know if this is an artist's rendition or what we're viewing, or if this is an electron microscope. I'm not sure, it doesn't really matter. But the point is you can observe 2 different structures here so that these 2 points are resolved. On the other hand, all of these points here are not resolvable. We might be able to tell that that's a different point than these, but there's an overlap. And then all of these we can't even break up. And that's because we cannot resolve the points. The points are too close together, and so we cannot distinguish them as 2 points. A light microscope has a resolving power of 0.2 micrometers. That means we can distinguish between 2 points that are 2 micrometers apart. That would be 200 nanometers. And anything less than 200 nanometers or 0.2 micrometers, you cannot resolve as 2 distinct points. Why we have this resolving limit to a light microscope has to do with the properties of white light. And white light's properties limit the resolution of a microscope to 0.2 micrometers. Even if you were to increase the power of a microscope, you would not be able to resolve these points because they're less than 200 nanometers apart, and the limits of white light will not allow you to resolve the points as separate points. Any questions about any of that? And it has to do with the wavelength of light. White light, you cannot magnify any greater than 2,000 times because the resolution limit is 0.2 micrometers. And that's having to do with the properties of the wavelength of light. The best compound light microscope we can make is a light microscope that has a total magnification of 2,000 times. Even if you were to get a more powerful lens, it would not be able to magnify more or greater than 2,000 times because of the limit of white light. Any question about any of that? All right. So that's resolution. Let's talk about refraction. Refraction is the light bending ability of the medium that light is coming out of. Meaning when light goes through a media and then switches to another media, meaning water switching to air, it causes light to refract or bend. And you can see that by looking at this pencil here, where it looks like the pencil is bending at the surface of the water. So this would be the artist's rendition, the pencil bending, and that would be the surface of the water. Now the pencil, obviously you pull it out of the water, it's a normal pencil, it doesn't bend. It's only appearing to bend because of the refraction of light, causing the light to bend at the surface of the water, meaning light refracts when it switches from one media to another if the media has a different refractive index. Any question about any of that? The refraction of light is extremely important to living things, like a bird. When it sees a fish in the water and the bird wants to catch the fish, the refraction of light makes the fish look like it's in this position. And that's because the water bends at the surface, or excuse me, the light bends at the surface of the water or the start of the air. And the fish is really down in this position. And so for living organisms that, like a bird that wants to catch the fish, it needs to know this is where I'm seeing the fish, but this is where I need to put my feet to catch the fish. Okay, any question about any of that? Now the refraction of light is extremely important when using the microscope because when light comes through glass of the slide and then leaves the glass and enters the air, light will refract. And some of the light will be refracted away from the objective lens. So it will not be collected by the objective lens. And that would be this ray here, which is refracted away. One reason for using oil with the oil immersion lens is that when the light leaves the glass and then enters the oil, oil has the same refractive index as glass, so the light does not refract, meaning it does not bend. And here you can see on this side, light is leaving the glass, and this beam of light doesn't ever even enter the air, at least at this angle, meaning it's refracted back into the glass. This one is refracted away from the objective lens, and so it will not be collected by the objective lens, neither will that one. And this one is refracted, but not enough so that this ray will be collected by the objective lens. Now, when we use oil, this ray and this ray will not refract, and so they will be collected by the objective lens. That means the objective lens will collect more light, and that increases the resolution of the specimen. So oil improves resolution by allowing you to collect more light, by decreasing the refraction of light. In this case, it's actually getting rid of the refraction of light. Therefore, immersion oil is used when you're using the oil immersion lens to improve the resolution. Any question about any of that? And this is why you use oil with microscopes, because it helps improve the resolution. If you don't use oil with the 100x objective lens, I mentioned it earlier, that the 100x lens will be no better than the 40x lens. And because the 40x lens is much easier to use, you should use the 40x lens. All right, here we're looking at bright field illumination where the specimen looks bright and the background looks bright. This is what most light microscopes are. All of the light microscopes in the lab use bright field illumination, meaning light comes through the specimen from the light source. The condenser puts a cone of light on the specimen, the light comes through, and that's why the specimen is light. And then the background is totally light because it's clear glass and all the light comes through. So the background looks white because that's the color of the light coming from the lamp. Any question about any of that? And this is showing you the path of the light. Now with dark field illumination, it's a little different, and we have an opaque disc. We have an opaque disc blocking the light that comes directly from the lamp, coming through the specimen, and then hitting the objective lens. Because the light is blocked, there's no light coming through the glass, how do I say that? There's no light coming through the glass and then going into the objective lens. And that's why the background of the glass slide looks dark. Dark field illumination, the background is dark. The specimen is slightly lit up, meaning it's a little darker than bright field illumination, but it is lit up. And what's happening is we have light coming from the lamp, striking the specimen, and the light that is not refracted will not be collected by the objective lens. And that's why the specimen looks darker here than in bright field illumination. So most of the light coming through, which is indirect, meaning the direct light blocked by the disc, the indirect light would not normally come up to the objective lens. However, when the light is indirect and then hits the specimen, some of the light is refracted by the specimen, and it's refracted into position to be collected by the objective lens. And that's why the specimen does look light, just not as light as this. And that's because it's getting some light that's refracted into position so that that light is able to be collected by the objective lens. All the light that is not refracted will be blocked by the opaque disc, and so it would be dark. And that's why the background looks dark. Any questions about bright field illumination versus dark field illumination? All right. Here we're looking at an electron microscope, and it does not use light. It uses a beam of electrons to view specimens. The beam is focused by electromagnetic lenses, so it's not using glass lenses. It's electromagnetic, and then the electrons have a charge to them, and so the electromagnetic lenses can adjust the beam of electron, and then we can collect it and then view the image. Electrons have a shorter wavelength than light, and that allows us to magnify many times more, about 100,000 times more, and it gives greater resolution, why we can magnify more. This allows us to see extremely small specimens like viruses, the internal structure of cells. You should know that there are two types of electron microscopes. There is a transmission electron microscope viewed here, and a scanning electron microscope viewed here. Let me blow this up. What do you notice between the two different types of electron microscopes? Transmission electron microscope, scanning electron microscope. What do you notice that's different?
The transmission electron microscope looks like it's in a lot more detail than the scanning one.
I'm sorry, I could hear part of that answer, but can you speak up? I'm afraid I didn't hear all the answer.
Yeah, sorry. I just said that the transmission electron microscope looks like it's in more detail than the scanning one. That's all.
That's not entirely true. It might be more, it's more detailed only because of what you're looking at. Here we're looking at the inside of the cell. Here we're looking at the outside of the cell. We have about the same magnification. So what else do you notice that's different? I sort of told you.
Are the backgrounds different?
I don't know why the background is different. No, the background really isn't different. I don't know why the background does look, come on mouse, why the background looks different. I don't know. I'll have to look into it. That might be just the background of this picture and the background of that picture. Meaning the background of this slide and the background of that slide. I don't know why the background looks different. So that's not what we're getting at. Here you can see we have about the sag magnification, 10 micrometers, 10 micrometers.
One looks at the internal structures and the other one looks at the outside ones based off of whether the beam passes through or off of.
Yeah, that's exactly one of the differences, the major difference actually, and that is the transmission electron microscope is showing you inside the cell, and it's a two-dimensional picture. Let me see if I can blow that up a little. So you're looking at only one plane of the cell, two-dimensional picture, but it's internal. The scanning electron microscope is only looking at the surface of things, the surface of this cell. Okay, and it is a picture in 3 dimensions. This is 3-dimensional, this 2-dimensional. Okay, that's the other major difference. Surface and inside the cell. And then the other difference, this is 2-dimensional, this is 3 dimensions. Okay, there are other types of electron microscopes, but we're not going to test you on them. So you don't need to really know them. I'll briefly discuss them, but you don't really need to know them. But you should know that transmission electron microscope allows you to see inside the cell in 2 dimensions. And then the scanning electron microscope allows you to see the surface of the cell, and it's in 3 dimensions. Here we're looking at another electron microscopic image, and this is a scanning electron microscopic image of a crystalline structure. And you can see that it's in 3 dimensions. This is a transmission electron microscope through a part of the plant cell. And I think this is the chloroplast membrane. And you can see it's in 2 dimensions. All right, any question about scanning electron microscope and transmission electron microscope? If not, let me state that there's also a scanning tunneling microscope. You're not going to be examined on this one. It's a third type of electron microscope. It uses a metal probe to scan a specimen. The resolution is very small. We can get to 1/100th of the size of an atom. Here we're looking at a protein from E. coli using scanning tunneling electron microscope. And then there's also atomic force microscope, electron microscope. You're not examined on that. It uses a metal diamond probe inserted into the specimen. It allows you to produce 3-dimensional images of what you're looking at. Here we're looking at a 3-dimensional image of the toxin from Clostridium perfringens. All right, here we're looking at some specimens viewed under the microscope. And which specimens are more easy to view? The ones on the left or the ones on the right?
The right.
The cells on the right are easier to view. The only difference between the cells on the left and the cells on the right the cells on the right are stained with a dye. The cells on the left are not stained with a dye. And this is showing you the importance of staining and allowing you to better see your object, or in this case, your cells. The reason why staining improves your ability to see the cells is only because the stain increases the contrast between the cell and the background of the slide, which is just a glass slide. So the only thing the stain is doing is increasing the contrast. And here, the cells are difficult to view because they have little contrast with the background, the glass slide. Any question about any of that? So staining doesn't improve the magnification. It doesn't really improve your resolution, that you still have a limit on how far apart you can see things. It's just that we're seeing them better when they're stained. And you do get better resolution when they're stained because the contrast has increased. How do I word that? If these were to become closer and closer together, you could still just see them as two distinct parts, two distinct cells, even when they're very close together. Whereas these, when they get really close together, it's really hard to distinguish that they're two separate points, two separate cells. Not just the contrast. So with bright field microscope, most microbes are colorless and have little contrast with the slide or the medium. To see cells, you therefore need a stain, or you could use a phase contrast microscope, which I have not talked about. You can read about it, but you're not going to be tested on the phase contrast microscope. The phase contrast microscope allows you to have contrast between the specimen and the slide. And what it's using is something similar to dark field illumination. It's not dark field illumination. It's phase contrast illumination. And it's paying attention to the light waves which are not being refracted and the light waves which are being refracted. And then it uses that to increase the contrast. And you don't need to know any of that because we're not going to talk about phase contrast illumination. But the point is to see cells well under the microscope. If you don't have a phase contrast microscope, you need to use a stain. Staining, all it does is color the specimen or the background of the slide to increase the contrast between the specimen and the background of the slide. So it's increasing the visibility by increasing the contrast. When you make a smear, you put your cells in a thin film on the slide. You use a thin film of cells in solution. And that's how you make a optimal bacterial smear. If you have too many cells on top of each other, you don't have a good bacterial smear, and it will be more difficult to get good resolution and be able to see your cells. Any question about making a bacterial smear? You need a very thin film of bacteria on the slide. Ideally, you wouldn't have the bacteria any thicker than 1 cell thick. And then to increase the visibility, you stain the bacterial smear. Usually when you're making a bacteria smear, you will air dry the bacteria and then heat fix them to the slide. This has the added advantage that this kills many bacteria, but not all bacteria. We'll talk about endospores later in the term. A cell that has an endospore, the endospores would not be killed by this air drying and heat fixing at all. Mycobacteria also would not be killed. And then some gram-positive cells would not be killed by this treatment either. At least not all of them. All right, let's talk a little bit more about dyes. Dyes are a stain that we use to see the specimen more clearly. The stains are all salts, meaning they have a positive anion and a positive cation and a negative anion. And that gives the salt a positive and negative charge. If the dye, or we call that the chromophore, is in the positive part of the salt, meaning the cation, the positive charge molecule is carrying the dye, we call this a basic dye. If on the other hand, the chromophore is in the anion, the negative part of the stain, then this is an acidic dye. Any question about any of that? Most stains in microbiology are using a basic dye. And the reason for most stains in microbiology to be basic dyes is bacteria have a slightly negative charge. Therefore, the cell tends to stain with a basic dye because the basic dye is positive charge. It's attracted to the slightly negative cell, and the basic dye will tend to stain the cell better than a acidic dye. And then crystal violet, methylene blue, malachite green, and safranin are all basic dyes. Any question about any of that? I'll show you a picture of a basic dye and a acidic dye in just a little bit, but let me talk about the acidic dye now. Acidic dyes have a negative charge to the dye, and that means the acidic dye is not attracted to the cell, because a negative dye will be repulsed from a slightly negative cell. Acidic dyes typically stain the background and not the microbe. Some examples of acidic dyes include eosine, acid fuchsin, and nigrosin. And these acidic dyes stain the background of the cell, and we call that negative staining. The term comes from the old Polaroid film where you had negatives to the picture, and the negative had, at least in black and white terms, the negative was the reverse of what you saw in the picture. And that's why we called it a negative. And we call it a negative staining because the cell isn't stained, the background is stained. Here you're looking at cells that are stained by basic stain. And here we're looking at cells that are stained by a negative stain. Both of the cells are pretty easy to view. The basic stain mainly staining the cell itself, and the negative stain mainly staining the background of the cell, not staining the cell itself. Any questions about basic staining and negative staining? Remember, a negative stain uses a acid stain. All right, if there's no questions about acid and basic stains, then let's move on to the different types of stains. There are three main types of stains: a simple stain, a differential stain, and special stains. A simple stain is when you're applying only one stain to the specimen. All cells will then pick up the same color. Talk about that in the next slide. Yes, I do. A differential stain typically uses two or more stains and stains the cells differently. Why we call it a differential stain. The differential stain can allow you to determine differences between cells or even within the same cell. A special stain is the third type of stains, and there are many different special stains. They are a stain for observing a particular structure in the cell. And we'll talk more about special stains in a little bit. All right, a simple stain is where the stain is it's a single dye, either aqueous or alcohol in solution. The dye is in either alcohol or aqueous solution, and then we use it to stain the cells, and we're only using this one stain, and that's why it's a simple stain. The primary purpose is just to increase the contrast between the background and the cell to improve the resolution. The stain is applied to a fixed smear, meaning you fix it and heat fix it, air dry it and heat fix it before you stain the bacterial smear. And then when you're staining it, you wash off the stain, dry it, and then examine it. All right, any questions about simple stains? If not, let's talk about a mordant. A mordant may be used in a simple stain. A mordant is just something that is used that intensifies the primary stain. In the Gram stain, the iodine is actually a mordant. We're not going to talk about the Gram stain yet because it's not a simple stain, but the iodine simply increases the ability of crystal violet to stain the cell. So it intensifies the stain, and it is by itself not a dye. In the Gram stain, we're using iodine as a mordant. The iodine itself does not color the cells. Iodine can be used when it's used on plants to color the carbohydrate areas of the plant cell. Actually, if you use it on something other than cell, it would show the carbohydrates of the organism as well. What crystal violet does is it increases the affinity between the stain and the specimen. And that makes the colored portion of a molecule larger, and then it'll be more visible under the light microscope. So mordant is not a simple stain. It just increases the primary stain's ability to see or stain the object. All right, any questions about mordants? A differential stain is a stain that reacts differently with different kinds of microbes. You can therefore distinguish between two different types of microorganism. The differential stain usually uses 2 or more dyes, but that is not required. All that is required is that the stain stains differently, different cells or objects. The most commonly used differential stains are the Gram stain and the acid-fast stain. They allow you to differentiate between 2 different types of cells. With the Gram stain, you're looking at gram-positive cells and gram-negative cells. And that's why the Gram stain is a differential stain. Any question about any of that? All right, the other commonly used differential stain is the acid-fast stain, and that allows you to stain for endospores. All right, let me just briefly talk about this slide. The Gram stain was developed in 1884, which you do not need to know, by Hans Christian Gram. And you should know this because when we write out the Gram stain, the G should be capitalized because Gram is the name of Dr. Gram, and we capitalize a person's first and last name. Gram is his last name. The stain that Hans Christian Gram used was differentiating between the patient's own cells and then a bacterial infection. So Hans Christian Gram did use it as a differential stain, but the differences he used were patient's own cells and then the bacteria infecting the patient. When microbiologists started using the Gram stain, they quickly realized that it classifies all bacteria into 2 very large groups. Those bacteria that are gram-positive cells and those that are gram-negative cells. So here, we're looking at a picture of cells stained by the Gram stain. And you can see dark purple cocci, which are gram-positive cells, and then pinkish rods or bacilli, which are gram-negative cells. Any question about any of this? All right, I think I will end the lesson here, talking about the Gram staining procedure next time. We're going to stop a little early because this is a good place to stop the lesson. And then I'll continue talking about the Gram stain next time. Let me make sure that we have 2. Oh, I can't do that. You're right. I'm supposed to finish chapter 3 today. We're not going to finish. All right, we're not going to break here because I only have one day for this lesson, and so let's continue. The gram stain procedure is shown here. You first make a bacterial smear on a glass slide. You normally allow the slide, the bacterial smear, to air dry and then to heat fix, and that allows the bacteria to be fixed onto the glass so that when you're doing the water washings later in the gram stain, that the cells are not washed off the slide by the water washing. This is giving you the procedure in a nutshell. First, you flood the slide with crystal violet. That's the primary stain for 60 seconds. You then wash with cold water. You dump the stain off and dump the water off. Then flood with iodine. Iodine is used as a mordant for 60 seconds. Dump the iodine off and wash with cold water. You then flood the slide with acetone and ethanol. These are decolorizing agent. You only use them on the slide for around 5 seconds. You then wash immediately to wash away the decolorizing agent. And then you flood the slide with safranin for 1 or 2 minutes. Usually with the safranin that are given in our lab, 1 minute is sufficient. However, you have weaker safranin, you want to stain it for 2 minutes to make it easier to see the cells, meaning the safranin, the longer you have it on the cell, the more darkly it stains the cells. And if the safranin is pretty weak, you might need 2 minutes. Usually in our lab, 1 minute is sufficient. You then wash the safranin off with cold water and then blot the cell dry and examine the slide under the microscope. Any questions about the overall procedure?
I have a question. So is iodine, like, is that the mordant for the counter stain?
Iodine is the mordant in the gram stain.
Yeah, but like, does it, because unless I'm confused, a mordant makes the stain, like, improves the stain?
It does make the cell stain a little darker. And I'll talk about that when I go through the gram procedure in great detail.
Okay, thank you.
Okay. All right, so this is showing you the gram stain in a nutshell. First, we stain with crystal violet, and all the cells stain purplish, a bluish purple. Then we apply the iodine, and all the cells still stain purple, but it's more of a purple, less of a blue purple. And yeah, the cells are slightly darker here than there, but there's no differences between the cells. We then use the alcohol wash. This is the decolorizing step where you're applying the decolorizing agent. And this pulls the crystal violet out of the gram-negative cells, but leaves it in the gram-positive cells if you're performing the gram stain correctly. This allows you to see differences between the gram-negative cells and the gram-positive cells. So this is the differential step. I'll mention that a little bit more later. And then we stain with safranin, and what it does is it allows us to more easily see the gram-negative cell, because the safranin gets into the gram-negative cell and then stains them pinkish or reddish. Any question about the overview? All right, so initially, you make the bacterial smear on a glass slide. Ideally, you have your bacteria only a single cell thick You do need to air dry and heat fix the cells. Otherwise, the cells will wash off the slide. You then flood this slide with crystal violet, which is the primary stain, for 60 seconds. Crystal violet will stick to the peptidoglycan in the bacterial cell wall. It's considered the primary stain, crystal violet, since it colors all cells the first time. You then do the water wash, and I forgot to mention this. Whenever you're going through the gram stain, you can, rather than state, I do a water wash, I do a water wash, I do a water wash, you can just state at the beginning or the end. After each step in the gram stain, you gently wash with cold water. Okay, that's all you need to do. Put it at either the start of the gram stain or at the end of the gram stain. You don't have to put in each, I wash with distilled water. Where were we? Oh, right here. So you wash with distilled water. After this step, all the cells, gram positive and gram negative, will stain purple from the crystal violet, and this will be a bluish purple from crystal violet. You then apply iodine to the slide, flooding the slide with iodine. What you do is, I guess I forgot to mention this, with the crystal violet, you dump the crystal violet off of the slide, wash with water, dump the water off the slide, and then flood the slide with iodine for 60 seconds. After 60 seconds are done, you then wash off the iodine with cold water, and you apply the water gently. All cells will stain purple, but because of the iodine, it'll be a more purple color for both the gram positive and gram negative cells. And when I'm in purple, it's not a blue purple color. And then you wash the iodine off. You dump the iodine off and then wash it off with the cold water. And now you flood the slide with acetone and ethanol. Hopefully you guys can see this. Where's my pen? Can you guys see this? I'm going to pretend this is a slide. The best way to decolorize is take a look at the slide and then apply the decolorizing agent on the slide. And when the dye, the purple, stops running, stop applying the decolorizing agent. That's the best way to apply the decolorizing agent. You're applying the decolorizing agent for only about 5 seconds. If you apply too much decolorizing agent, it will remove crystal violet iodine from cells it should not. And if you do not apply enough decolorizing agent, you will not remove the crystal violet from all cells that it should be removed from, meaning the gram negatives. You should then wash immediately, well, dump the acetone ethanol off, and then wash immediately with crystal violet. I never stated before, wash immediately, because it's not important on all the other steps whether you wash immediately or not. You do need to wash immediately after the decolorizing step, because even when you dump the decolorizing agent off the slide, there will be decolorizing agent left on the cells, and that decolorizing agent will continue to work. And you don't want it to work any further, so you wash immediately with cold water. Any question about any of that? All right, after the decolorizing step, we can now see a difference between the gram-positive cells, which will stain a purple color, and the gram-negative cells, which will stain colorless, meaning the crystal violet iodine, which forms a complex, has been washed out of the cells. Any question about that? The decolorizing agent is the differential step, allowing you to see differences between the different cells, meaning allowing you to distinguish between the gram-positive cells and the gram-negative cells. You then apply safranin. Safranin is a pinkish dye. It gets in all the cells, so it stains all the bacteria. It is a counter stain because it has a different color to the primary stain, meaning it has a different color than crystal violet. You apply the safranin for 1 to 2 minutes, and then you dump it off and wash with cold water to remove the safranin. Any question about any of that? After applying the safranin, the gram-positive cells stain purple, and it's a purple color, and the gram-negative cells stain a pinkish color. You then wash the safranin off and observe your cells. All right, here's a question for you. If safranin stains all bacteria, and I just told you it gets in all bacteria, why isn't it staining the gram-positive cells pink? Why does it look purple to our eyes?
Does it have to do with the moderant?
I didn't hear that. Can you say the last part again?
Does it have to do with the second step, the moderant?
Has to do with the second cells?
The second step in the gram stain?
Oh, the second step.
Yeah.
Well, the second step is, I don't think you meant 2 here. Are you
No.
talking about staining safranin? As the second step?
No.
Anyways, I'm going to say no. It has nothing to do with the gram stain. It all has to do with our eyes. The safranin does get in the cells. However, the pinkish color is a lighter color than the purple, and our human eyes only see the purple. To see the pink, we would have to look at the cell under the electron microscope and blow it up many times. So if this were the cell, you would see one area of the cell staining purple under the electron microscope, and then another region of the cell staining pinkish, where the pink dye is. But under our eyes, it's just the property of human eyes, the pink is a lighter color than the purple, and so we do not see the pink color with our human eyes. Okay, but the pink dye is there in the gram-positive cells, but to see it, you'd have to blow up the cells many times with an electron microscope. Okay, any question about any of that? All right, you then blot the slide dry with bibulous paper. Bibulous paper is sort of like cardboard. So here, this is my slide. I hope that you can see this. And then you fold the bibulous paper over, and then you just press the bibulous paper down. You do not take the slide and wipe it on the bibulous paper, because that'll pull off the cells. You just blot it dry. And then that'll be dry enough to see the cells under the microscope. Even if you use oil, that will still be good. All right, let's stop here and I'll ask, are there any questions? If not, I will see you in the lab at 6:30.